Hey, welcome back to Fat Mama Physics. In this video, we're going to do questions 8 and maybe 9 from this worksheet that we have over here for double slit experiments. So, without further ado, let's begin. Question 8. Find the distance between adjacent dark spots from a double slit diffraction pattern if the wavelength of light is 500 nanometers, that's roughly green light. The distance between the slits is 1 millimeter, and the distance from the slit to the screen is 2 meters. So first thing I would do is I would draw a diagram. So to draw this diagram, okay, we're going to first start with the slits. Okay, we have these slits over here. The distance here is 1 millimeter, and to the screen is going to be about 2 meters. Okay, we want to find the distance between adjacent dark spots. We're given the equation for bright spots. Okay, so that's bright spots, okay? But, yeah, what about for dark spots? Does it work the same way? In fact, it does actually work the same way. This equation here, S, lambda, big D, and small d, works for both bright spots and dark spots for a double slit interference pattern. Because if you take a look at the spacing between the bright fringes for this one, the dark fringes are going to be here, and they are pretty much relatively going to be the same distance as you move further away from the central band in comparison to the bright fringes. So the spacing is the same for the bright as for the dark. So guess what? You can really just use the same equation. This one does assume that the pattern that you produce is roughly going to be repeating, meaning that there's not going to be it's not going to widen out, it's not going to condense itself, it's going to be uniform across the board. So that's what it assumes for double slit experiment. That's pretty much what you need for standard level. HL, it's not going to get too tricky from there either. Okay, so let's begin. We have a few things we're given. We're given our, that's question 9. So wavelength is here. The distance between our slit is small d, so that's this guy over here. Distance to the big screen, that is the big D. So all we need is those 4 numbers to figure out this the spacing between even the dark spots. Okay, so we'll get 500 nanometers over here. Okay, and then we're going to get the big distance, which is the 2 meters. And then the bottom, we're going to have 1 millimeter here on the bottom. So when you put this into your calculator, you just have to make sure you do the proper conversions. So for example, 500 nanometers, I'm going to type 500 to the power of -9 because times 10 to the power of -9 times 2 divided by 1 times 10 to the power of -3 for millimeters. I get 0.001 meters. That is roughly 1 millimeter, essentially. 1.0, how many? Yeah, that's about 1 sig fig. So 1 millimeter. That is, leaving in meters is fine as well. Okay, that's question 8. Woo, that was pretty fast. Guess what? We're going to do question 9 in the same video. Okay, so in question 9, in the double slit experiment, it is found that blue light of wavelength 467 nanometers gives a second order maximum at a certain location on the screen. What wavelength of visible light would have a minimum at the same location? Ooh, this one is tricky. Okay, so we're going to draw a picture first. So let's draw this one in black. Okay, so first of all, let's draw the bright fringe in the middle, and then the successive peaks like this. Very ugly. Okay, let's say this is the middle. When they talk about order in the question, when we say order, we say that the middle has an order of 0. Okay, what that means is, think about the order as in the wavelength difference, the path difference between the 2 slits to that point. So, if I have 2 points of light, point sources, and they're shining at this point, basically the path difference between these 2 light waves are going to be the same. The wavelength difference is 0. But if we produce this peak right beside it, essentially what's going to happen is one of the paths is going to travel exactly one wavelength further than the second path. So we say that the difference is one wavelength, meaning we're going to give this order of 1, and this one 2, and etc. This one, it will just be 1 and 2, but the other light would have traveled the further distance instead of this light. So it's kind of similar. And mathematically, it might give you negative values, but I mean, really, the negatives and positives, as long as you figure out what the problem is trying to do, you can manipulate that yourself. In a double slit experiment, it's found that, okay, so the second order maximum is certain location on a screen. Okay, so blue light, hey, I'm going to use blue here. So here, the second order, blue light with wavelength of 400 and how much? Of 67 nanometers gives a second order maximum here, okay? We want to find, what is it? Something that's going to give us a minimum. Okay, so these will be your blue fringes. What it means to make a minimum at that point is imagine that this next light could be red, we don't know. Imagine it, there's a couple of possibilities. One of the possibility is it would have gone through the middle, which is going to make a peak, okay? Everything's going to make a peak in the middle, unless you have two sources that are out of phase. But essentially, you're going to have this. So that's the simple case. That's a simple case where this is going to be a minimum for, let's say, red light or something like that. Maybe it is red light, we'll find out. So that could be, so for dark fringes, again, this would also have an order of 0 because it would be exactly half of a wavelength, which then when we use m plus 1/2, m would just be 0, meaning you'll just get half a wavelength difference. So that would give us an order of 0 if that's the case. The other possibility here is instead of this being, I'm going to use a different color here. Let's say it's green. Okay, imagine another possibility is this instead of wouldn't be the first minimum after the bright peak, it will be the second minimum after the bright peak. So I kind of have to squeeze it like this. So it kind of goes down to here, and then back up, and then back down again. Okay. Oof, that's a very crazy drawing here. So maybe what I'll do, so you kind of get the idea. So imagine there's another possibility here in which instead of the first minima hitting that second order for blue light, it's the second minimum. Okay, so originally we would say that for the red one, the first minima has an order of 0, and then it will have an order of 1 over here, etc. For the green line, the first order for the dark fringes would be 0 here, and this guy would be 1. Okay, so there are a couple of different. There is two different possibilities that could happen. So we're going to have to try for both because we want to find a wavelength of light that falls within the visible light range, which is roughly from about 400 nanometers to about 700 nanometers. Anything above that or beyond that is going to be outside of the visible region. So let's do the red case first. Now for the red case, we're going to go back to our trusty equation here. And let me explain a little bit what this wavelength here means. Imagine this wavelength is the number of wavelength in terms of path difference between the two sources when they arrive at that point. So every time we've done this question, we've treated the S, the spacing, as a spacing between two successive bright or dark fringes, in which the wavelength difference would be either by a whole wavelength. Okay, because if you take a look at question 8, for example, the path difference between here and this bright fringe here would be exactly half a wavelength. This, from one of the point sources, would have traveled an extra wavelength from here versus there. For dark fringes, one of the wavelengths would have traveled 0.5 of a wavelength longer than the other one. At the next dark fringe, that particular light source would have traveled 1.5 wavelengths more than the other path. So again, it's also difference by a full wavelength, going from one space to the next space. So what we have to do here is that we have to compare not one space, but two spaces to the bright fringe. So we're comparing this distance over here, in which what we have in terms of the spacing from the middle to that point, from the second order blue light, is exactly 2 wavelengths of difference. So we kind of have to modify this equation a little bit here, in which the blue light, okay, hey, I can use color here, is S is equal to 2 wavelengths times whatever distance to the screen is, and the spacing between the slit widths. Now imagine if I am going to compare that with the red line. So imagine if the red line was the possibility there. Then in terms of the spacing, this spacing here would be exactly half a wavelength difference. In order to get a destructive interference at that point, the path difference would have to be half a wavelength times the distance to the screen divided by the distance between the slit widths. So what we know for these two relationships is that the spacing from the middle to that particular point on the screen is going to be the same. So what I'm going to do here is I'm going to equate both of these equations. Okay, 1/2 lambda, big D, small d. And here a few things are going to cancel out. This d is going to cancel out, this d is going to cancel out, as well as this one. This lambda here is for blue light. So I have to write down 2 times whatever's 467 nanometers. And this is going to be equal to a half of whatever this wavelength is, because it's destructive interference. And if I just work this out, if I try to calculate that lambda, which is what the question is asking for, times 2, I am going to get a whooping 1,868 nanometers, which definitely lies beyond the visible light range. Probably, what's that, infrared, or even greater than that? Yes, I forgot. But anyways, this is definitely not within the visible light range. So we have to look at the green line, perhaps, because we need a smaller wavelength than that. So again, the spacing for the blue light is going to be 2 spaces, which means the path difference is of 2 wavelengths. So 2 wavelengths and times this, so that's going to be the same. However, for the green one, okay, the same spacing is going to be not half a wavelength, but 1.5 wavelengths. 1.5 wavelengths times the same thing, everything else is the same. So the same spacing for the blue light is going to give us 2 full wavelengths. For the green one is going to give us 0.5 of a wavelength because it's destructive interference. We're going to equate these two again. So that's going to be over here equals to 1.5 lambda big D over D. So a few things cancel, including these big D's. And we know that the blue wavelength there is, again, 467 nanometers. And this is going to be equal to 1.5 of this wavelength. So let's calculate this wavelength here. 2 times 467 nanometers. And I'm going to divide by 1.5 on both sides, right? Because that's going to give us what we need. And this is going to give us, ooh, hey, this looks nicer. 620 rounded up to how many sig figs? Maybe 3, I suppose. About 3 sig figs. So 623 nanometers, which is within the 700, roughly 700 nanometer range, and the 400 nanometer range. Okay, so definitely 623 nanometers is our answer. Okay, phew, all right, so that was definitely a trickier question. It kind of tests you whether or not you fully understand where this equation comes from, how is it kind of derived, and just fully using these concepts here. If you got all of that, if you learned a little bit from this video, awesome job. I hope this video is going to help you do some of your other examples. Good luck, and Fan Mama Physics signing out.